So, before understanding what happens in the 10 steps of glycolysis, we just need to keep in mind a few ideas. First, that overall, we have 6 carbons in glucose. There's no CO2 released. What does that mean? That means That means that we have to account for all the carbon atoms at the end of glycolysis. It's a very important idea. Also, glycolysis can happen with O2 or without O2. Without O2, it will just happen normally. With O2, you can. That's the general idea, that you can just grab the energy directly from the products of from pyruvate directly. That's it, and not H. If there is no oxygen, it'll just keep happening and storing the byproducts for different cycles later on, or it can keep regenerating them, like for instance in case of fermentation, and for animals that hibernate in brown fat cells. I think it's mentioned at the end. So, and one more thing to keep in mind is the tally, the sum of everything. So we will form 4 ATP and 2 ATPs are used. 2 NADHs are reduced, meaning they will accept electrons and H. Each NAD accepts two electrons and 1 H and releases the other H. So we just have to keep in mind. Another very important idea: glycolysis happens in the cytosol, in eukaryotic and prokaryotic cells. What else? That's it. Another idea before going through the steps is that the first 5, they consume ATP, they consume energy. After the 5th step, meaning what happens at the 4th and the 5th is that glucose is broken down into 2 molecules, 3 carbon atom molecules. 6 and forward, we will start regaining energy in the form of 2 NADH and 4 ATP. So let's go. The steps. Steps here. The first step, we have the glucose, of course. We have the first kinase. Another idea in the 10th steps is that whenever there is a kinase, expect a phosphate group to move about. Since we already established that the first 5 steps we always lose energy. Energy is always consumed. What does that mean? That means whenever there is a kinase, a phosphate group is taken from ATP into the molecule. So kinase here will grab a phosphate group from ATP and attaches it to glucose. What's the point of this step? Why does it do that? Because glucose 1, is it 1? Glucose 6. Glucose 6 phosphate is less stable, is more reactive, can be more easily changed, morphed into something different. And the first step is where we use the first ATP, and there is another purpose or another role that this step serves, is that it traps glucose within the cell. It can no longer be easily it just traps it. That's it. What do we get? We get glucose with a phosphate. It's called glucose 6-phosphate. Then we will need we will change this glucose into fructose. It's called phosphoglucoisomerase. Why is it called phosphoglucoisomerase? Because isomerase changes the formation, the configuration of the sugar. Why is it called phospho? Because the glucose that we have has a phosphate group. That's it. Now we have fructose 6-phosphate. The shapes are different. As we know, just like how fructose and glucose are different. That's why we have 1, 2, 3, 4, 5 instead of 6. That's it. Then next step, it's an important step because it's the second time and the final time ATP is consumed. We grab a phosphate group from ATP, turning it into ADP, and that phosphate group will be attached to the fructose 6 phosphate. That means it will have 2 phosphate groups. It's an important step in the regulation of glycolysis. But I don't know why they mentioned it, but it is. That means the name is gonna change, and as we already know, it's a kinase. So it's a phosphofructokinase. It moved, it grabbed the phosphate group, attached it to the molecule, wherever it is. In the first step, it's a hexokinase, because glucose is a hexagon. And the third step, it's a phosphofructokinase. Now we have the final. What's so special about fructose 1,6-biphosphate? It's the final product that has 6 carbon in its structure, because the fourth step, aldolase will cleave the fructose 1,6-biphosphate into G3P and DHAP. And those two are the first 2 3-carbon products which will later on become pyruvate. However, pyruvate does not have phosphate groups in it. These 2 products, they each have a phosphate group. That phosphate group came from an ATP, first step and third step. It wouldn't matter because it's going to be cleaved and each of them will have phosphate group. However, only G3P will continue with the steps. This is more of a regulatory step. Instead of creating 2 G3P, we have G3P and DHAP. Now we're done with the energy consuming half of glycolysis. There's nothing else to say here. The fifth step is one that changes DHAP into G3P, and only G3P will proceed with the rest of the steps in glycolysis. They mentioned that this change, and it's also called an isomerase, T-hap isomerase, whatever. This will never reach equilibrium. So based on maybe supply and demand or availability and whatnot, they will continue being exchanged. So 6 steps. Now, regarding those steps here, few ideas we need to point out. First, the end product is pyruvate. Pyruvate, we get 2 pyruvate bases because each pyruvate has a 3-carbon structure, and we started with glucose, 6 carbons. No pyruvate, no end product should have phosphate group. So pyruvates don't have phosphate groups. This second half of glycolysis will provide us, as we kept in the back of our heads, 2 as a final product, 2 ATPs as a net gain, and 2 NADH. Now, in the first half we consumed 2 ATPs, so now we need to look for 4 ATPs and 2 NADHs, and we should look for kinases. Kinases in the second half of glycolysis will phosphorylate by substrate level phosphorylation. They will substrate level phosphorylate ADPs. Also, we have to keep in mind that now we're dealing with 2 molecules, because each is a 3-carbon molecule, G3P, 2 G3Ps, and the end product is 2 pyruvates. So, like, we can imagine that there is another parallel duplicate process happening here. First one is a triose phosphate dehydrogenase. It's called triose because the G3P is 3 O's, 3 oxygen thing. Now, phosphate, because G3P has a phosphate, each has 1 phosphate. Dehydrogenase, because it's called dehydrogenase, it's gonna rub G3P of hydrogen atom, as in it will be oxidized, and what will be reduced? It's the NAD plus. So triose phosphate dehydrogenase will act on 2 G3Ps, two sequential reactions. Yep. Yes. Okay. Where did we get those from? If we remember, we used up 2 ATPs, so now we have 2 ADPs and 2 inorganic phosphates in the solution, in this whole process. We also have 4 electrons, 4 hydrogens. Where do we have those from? Where, remember that the first 2 will be taken from G3P directly, and the other 2 will be taken from each ATP. Not from, I mean, from the step where ATP is used. because the phosphate group from ATP will replace something in the molecule, and that something is the H. So 2 ATPs used, 2 H pluses are available now, and the other ones, the other twos, are grabbed from G3P using triose phosphate dehydrogenase. Okay, excellent. Now, if we remember, G3P, each G3P has one phosphate group, and we have 2 inorganic phosphates floating around. We will grab each and attach it to a G3P. It's an instead of using the enzyme just removed an H and attached the inorganic phosphate to it. Now we have the first kinase here, and since we know that kinases are involved in moving phosphate groups, and that the second half of glycolysis produces ATPs, each G3P will be kinased, and it's called phosphoglycerokinase. So it's as opposed to hexokinase and phosphofructokinase. Why 2? Because again we have 2,1,3-biphosphoglycerate. And that's the first instance of ATP formation, substrate level phosphorylation. We will end up with a 3-phosphoglycerate. Kinase will only remove 1 because it's a multi-step process. We don't want the burst of energy to happen. This is the first instance of a mutase. What does a mutase do? It just relocates stuff. It will relocate the phosphate group. Why will it do that? In order to strengthen the bonds and make sure that no H's are lost and only the phosphate will be lost. Only the phosphate will be worked on, so that we can end up with a double bonded CO pyruvate molecule, like 2 double bonded CO as a final product, which is the pyruvate, which is a high energy molecule, and we can see that because these bonds are very strong here, and generally that's the whole purpose of the operation. It's not providing ATP, but it does, just in case of for many reasons. For humans, maybe in perfect conditions, we would not need these ATPs, but glycolysis doesn't only serve as a precursor to the next processes. It also it can also be used as the sole source of energy in case of fermentation and for animals or creatures that hibernate. Now, after the mutase, we have a new enzyme, which is enolase. Now, enolase will create what's so special about enolase and the subsequent product? It's that PEP which is done on the 9th step by enolase. It's the last product in glycolysis that has a phosphate group. Enolase does a very important thing. As we mentioned before, it's the double bonding between oxygen and carbon to strengthen the structure and to weaken the only part of the molecule that we need to dispose of to get pyruvate, which is the final phosphate group. Enolase creates the PEP, which is phosphoenol pyruvate. Yes, PEP has the last phosphate group. We have 2 water molecules here at least. And finally we need a kinase, which is a pyruvate kinase. Pyruvate kinase acts on the PEP to provide us with the pyruvates, 2 pyruvates for each glucose molecule. So pyruvate kinase will turn PEP into pyruvate and 2 ATPs as the phosphate group from each, and that's just about it.